Hello, this is how to use the GNU debugger GDB for KDE programming. On Google, I searched KDE Wiki GDB, the first link in here. We are programming KDE applications. We're mainly using the Linux operating system. GDB is part of the foundation of the operating system. Let's see how we can use it. So we can either start an application using GDB, or if the application is already running, we can attach to it using GDB. Or if the application has crashed, which means that the application has encountered an error that has stopped the process. If that crash creates a core file, so a image of the random access memory of the process while the process was crashing, written to the disk, then we can use GDB and we provide the core file, and it's going to show us what the application was doing while it has encountered that fatal error. We are going to use the KDE application kwrite. For this, we're going to actually build kwrite using KDE Builder to make sure that we have full debug symbols. In this case, we're going to use complete debug symbols for all of the KDE libraries and applications, not for the Qt framework. And if you want to know how to do similar things when you don't have enough debug symbols, then that would be a advanced topic and another material. So let's first build kwrite. I have KDE Builder already installed, so let's make sure it's up to date enough. And now we can start building. The kwrite application is a graphical user interface application from the KDE community, but the KDE Git repository is actually the one for the Kate application. So the same KDE Git repository contains both Kate and kwrite. So we want to build the Kate KDE Git repository. 46 Git repositories are going to be Git cloned and then configured, built, and installed into /kd/usr directory. Thank you for subscribing and helping this YouTube channel. Let's first make sure that the KDE Builder build framework is configured to create executables that have full debug symbols. So for that, we're going to look at the configuration file of KDE Builder. And under CMake options, we should have -d, and then CMake build type equals debug. The default value in here is rel with debinfo, which contains some debug information, but there's optimizations for a build of type release. So I have changed rel with debinfo with the string debug, which will create the best builds for debugging purposes. The build has finished. It was an incremental build, not a full rebuild. Let's see if we can run the application. So KDE Builder --run and then kwrite. And it works. And we're going to not use KDE Builder --run to run kwrite to start the process, but actually we're going to do the two-step process, which is first we're going to source a number of environment variables. So that's in the build directory, tilde/kd/build/kate/prefix.sh, and then the path environment variable is going to be modified such that the kwrite that was installed into tilde/kd/usr/bin/kwrite takes precedence over all of the executables that exist, for instance, in /usr/bin. So I have multiple Kate installations on my system. I have one installed from my Linux operating system, which is Kubuntu 2604, which is this one, /usr/bin/kate. But then I have also built Kate using KDE builder, and it's in the directory that we have expected, which is tilde/kd/usr/bin/kate. At this point, if we just run kwrite, the correct kwrite should run. So this one, and with the correct environment variables such that it finds the correct configuration files, data files, libraries, etc., plugins. Okay, so we could run kwrite from the command line, which is important because we're going to do the first type of action with the GDB, which is we start the application from the GDB command line. So that's GDB and then the name of the executable. Okay, the process has not started GDB, it has just found the correct executable file, so ELF file named kwrite in the search paths, and it has found the debug symbols of this executable file. Next up, we can provide command line parameters to kwrite, which can be done like this. We go set args. We're at inside the GDB REPL, read, evaluate, print loop. We can see that because we can see the GDB between round parentheses prompt. And in here, we can run commands that we can run inside the GDB REPL. Such a command is set args and then the rest of the command line of kwrite. So the first part of the command line of kwrite is here, and the rest is going to start from here. So if you want to start the process kwrite space myfile.txt, that's going to be done in 2 steps, GDB space kwrite, and then set args space, and then the rest of the command line, which is myfile.txt. The process did not start yet because we didn't tell GDB to actually start the process. And since we have the kwrite executable with its debug symbols loaded inside the GDB, we can create breakpoints. So we say create a breakpoint at the symbol that that's C programming language symbol named main. And because the kwrite executable has been built using debug symbols and no release optimizations, it can find the actual source code of the main symbol and its line. So says main.cpp from this directory and then line 24. So it put a breakpoint actually in here. And it's the first breakpoint. And now finally we start the process. So we say GDB start the process, run. Today we're not going to use debug info-d because we're debugging kwrite, which we have just built using KDE builder. The rest of the KDE libraries are also built as dependencies by KDE Builder. So we don't really need to get debug symbols from our Linux operating system using debug info-d. This might come in handy for the other libraries, so non-KDE libraries, such as, I know, glibc, Qt libraries, etc. We're going to always not enable debug info-d for this session. So either press enter, because N is the default option, or press N and then press enter when it asks if you want to enable debug info-d for this session. So the process has started and thousands of instructions in the process have been run. And then breakpoint at line 24 in main.cpp was reached, at which point the GDB debugger has paused. And now it informs us that GDB is paused at breakpoint 1.1, main.cpp, line 24, and then the current function that we're in is the function main with two arguments parameters. This argc, which is the count of command line parameters, which is 2, and argv, which is the rest of the args. Okay, we can put additional breakpoints. All of these things that you're seeing right now are on the blind. You don't actually see the source code file. When you use a debugger, you probably 99% of cases are using an integrated development environment or a very fancy text editor where you have GDB integration. So you can actually put breakpoints by going to the line that defines the body of the KAboutData constructor and put a breakpoint there. You don't actually need to run GDB commands, but you actually can see the source code. So you can reason why we would want to put a breakpoint in the KAboutData constructor. Right now, you don't even know that there's a call to the KAboutData constructor in kwrite because you're not even seeing the source code. So let's just blindly do what it says in here. Okay, at this point, we have two breakpoints. One at the very entry of the body of the main entry point main function, and another one at the entry point of the constructor, at the body of the constructor of KAboutData. Okay, continue will run as many instructions as possible until another breakpoint, the next breakpoint is being hit, touched. Instead of continue, you can write just C. Let's see that in the help. So says that continue, F, G, or C do the same thing. Run the program. You can also provide a number of how many times to run the command continue. So you can use a syntax like C and then 4 to run the command continue 4 times. Okay, so let's see what it says. It says that it has hit the breakpoint 2, which is the body of the KAboutData constructor. And these are the arguments parameters to the constructor. Some of these are native Qt types, such as QString, and are more advanced C++ types, which GDB by default cannot display. But we'll see further how we can teach GDB to also display some of the most important Qt types. Okay, we can see the source code of the place where we're paused inside the debugger, which is line 630 from kaboutdata.cpp, either by clicking, in this case, or control click. Console knows how to open a full plaintext file path colon a line number, goes to line 630 of the file, the correct file. Or you can use the GDB command list, which is going to write source code lines centered around the current line where we're paused inside the debugger. So we're at line 630, currently 630, and you can see the some previous lines and then some next lines. In total, there's 10 lines. So the current line, and then 4 lines after, and 5 lines before. In total 10. If you want to display more lines, there's a command line parameter to list to increase the number of lines that you're going to be shown. Okay, let's see what the tutorial says. So it says, don't list whatever is the current source code file, which is kaboutdata.cpp. Actually list a totally different file and at line 200. Let's see how that works. So it says that there are multiple main.cpp files, and the one that GDB knows about, which is tilde/kd/src/kate/up/kwrite/main.cpp, the source code file of the other breakpoint and of the entry point of the executable of the process, and also the other place in the core stack, is shorter than 200 lines. So we can list also with the full path. You must specify a colon and then a line number. Only like this, it considers that this is a file path or a file name or a relative file path, and then a line number. Otherwise, it's going to think that this thing might be a symbol inside this executable or its libraries. So in this case, a free function. Okay, we can put a breakpoint in the current file. So in main.cpp, for instance, in line 118 here. The syntax break and then line number. You can always look at the help space break. Instead of break, you can use just B. And we have used a number, which is probably this command line parameter location. And you have very advanced functionality like the breakpoint should be conditional. Or from a symbol, you can do pointer arithmetics, etc. There's advanced features when setting breakpoints or watchpoints. Okay, so now we have 3 breakpoints. Let's continue. And it has encountered the second breakpoint a second time, which is the constructor of kabout data. Okay, so at this point you can continue, or you can stop the process. For instance, you can exit using exit, or quit, or Control D. Next up, we're going to start the kwrite process. And after that, we're going to start the GDB and attach to a existing process. So let's do that. We start kwrite. And we can either stop using this terminal tab because we have opened kwrite in the foreground, or we can background the process, Ctrl Z and then BG. Or we could have started from the start kwrite with an ampersand at the end to release the current shell instance, the current tab in the terminal window. Or we could just use a different terminal to do the GDB command lines. So first of all, we need to find the process ID of the process kwrite. And it's this one. So 1,028,879, which is a huge process ID number. Have 1 million processes actually run on this computer. Okay, and GDB kwrite will fail because I don't have kwrite installed from my operating system. So I actually need to have kwrite in the path environment variable. And for that, we're going to need to source the prefix again. So KDE build Kate and then prefix. Okay, so GDB, name of executable, kwrite, and then process ID. Okay, so it could find the kwrite executable file, which is this guy. It could load it. It found debug symbols. We're not going to page, so we're going to press C to continue without paging. We're going to not use debug info D and enter. And let's see what it says. I'm not sure what it says. If you encounter this error where it says bit trace operation not permitted, And then it talks about YAMA, so YAMA. The fix is to decide that this is a developer computer and you don't need the protection against pit race. So you don't need this security hardening for this current computer. You're going to disable this hardening named YAMA pit race, either until the next reboot with a command line like this, echo 0 and then piped sudo to become super user to be able to write this file, and then T and then this file, /proc/c/kernel/yama/pitrace_scope, or there's a way to make this change persistent even if you restart your computer. And that's done with cctl and configuration files in /etc. I already have run this command line, that's why I didn't encounter the YAMA issue. Next up, so I said that we pressed the keyboard key C to continue. And the process is actually running and it's not paused in the debugger. Or not. Yeah, the process is paused in the debugger. That's why it said something. Okay. If the GDB debugger is paused, you can look at additional information. You can look at the stack trace, which is the current function where the execution is paused, and then its arguments, the arguments of this function, and then the caller of this function with its arguments, the caller of that function with its arguments, etc. So there's a stack with function name and then argument name, argument value, with a source code file and a source code file line number. And then there's additional information because again we're paused. We can see the number of threads that currently exist. We can see a stack trace for each of those threads in the current process in kwrite. We can inspect the local variables available at the place where the execution is paused, the members of the current object, global variables, environment variables, command line of the process. Okay, we're going to ask for GDB to show us the backtrace, the call stack of the current thread. The GDB command is bt. So it's showing a stack trace, a call stack for just one thread. This is how it works. It's a stack. It's first in, last out. So the first in was the entry point of the executable, which is the function main. This time we didn't specify a file that kwrite should open. That's why arg count, argument count is 1, not 2. And this is the place where the call was made. So this is the outermost caller, function caller. So line 162 of main.cpp. And in here, another function has been called, which is this application exec, probably static method, which is this thing. We don't have symbols for it because we don't have symbols for non-KDE source code. This is Qt source code. It knows at least that at that position there's a method and its name, but it doesn't know the source code file where this body was defined of the method exec, neither line number. So this is incomplete call stack information. And then qcore application exec called another Qt function, which is qEvent loop exec, incomplete without CPP source code file name. And then that called another Qt function, process events method from qEvent dispatcher glib. Glib being the GTK base library where the main loop lives. Qt applications, KDE applications, GTK applications use the same main loop, which is the glib one. Okay, and now we're in glib, libglib, gmain context iteration, and then another symbol from the same library from glib, and then that goes to the operating system backend part of the main loop. So the actual implementation for our operating system, which is Linux Ubuntu 2604, using the interface between user space and kernel mode. We don't have debug symbols for these. We don't have debug symbols for the GTK library glib, and also debug symbols for Qt. Again, we have complete debug symbols for all of the KDE symbols, all of the KDE libraries and executables. Why are we inside a main loop, inside the glib gmain context iteration? Because that's how graphical user interface applications and their toolkits have worked in the last 30 years. There's a main event loop that waits for events to happen, waits for the user to move the mouse, waits for the user to touch the screen, waits for the user to press Alt F4, etc. And then when an event is incoming, the main loop asks, hey, is anyone interested in this event? And if so, it dispatches this event to all of the interested parties. Event-based programming. So that was the second way of starting GDB. The process kwrite is already started and we're attaching using GDB to a running process. The third way to do it is to have a core file that was generated either because the process has crashed and there's infrastructure that when processes crash, core files are generated automatically, or we can monitor a process and when it crashes, we'll create a core file. Or we can monitor a process and tell the process, hey, please crash for demo purposes such that we get a core file that we can use using GDB. Okay, so let's exit GDB, Control D, Y, Enter, Control L, and depending on your Linux operating system, the steps might be different. One of the important parts here is that probably you want a large ulimit for the core file size. On my operating system, there's no limit. Core file size is unlimited. And then if that's the case, you're going to decide how you want to create the core file. We're going to start the kwrite process and we're going to tell it to crash by sending the Unix signal segv. So kill all space minus all uppercase segv and then the name of the image of the process. But then who will create the core file? You can either configure your system to create core files when processes crash, but in my case, I don't need to actually configure anything because the systemd subsystem systemd minus core dump is enabled, installed, and configured out of the box on this operating system. The setting that you're interested in is looking at the configuration file /proc/c/kernel/core_pattern. And in here you can see that whenever a process crashes and the kernel mode might want to create a core file, it should call this command line. So systemd-core dump, and then all of these parameters will be populated. I don't know, maybe %p is the process ID. So whenever our process kwrite will crash, this executable will run and will create a core file. So let's do that. We're in the tab 3 in this terminal. We have sourced the prefix file in here, which means that we can start kwrite. So we can start kwrite. Let's actually close the existing one. You can start kwrite like this, which doesn't free the current bash shell. You can run it like this, such that the process, it gets backgrounded and you get back access to your bash prompt. And in this case, because there's KDE frameworks and other functionality related to detecting when a process crashes, when there should run a bug reporting tool, we want to use this environment variable kcrash_dump_only and then 1 to disable all additional functionality. Just a dump file will be created, a core file. Okay, we get back access to the bash prompt because we run kwrite and then the ampersand. We're going to kill the process. Let's see how it dies. So this window should disappear. And it took half a second to disappear. The systemd-core dump subsystem of systemd has this executable named core dump ctl. Let's look at its help file, and in here we have the option of seeing the available core dumps or getting more advanced information about existing core dumps. So let's run all of these. Core dump ctl list. So there's a ton of core files, and it's really important that your run of core dump and output line from core dump ctl list says core file present. Okay, as you can see in the help, it says list and then matches. So you can specify part of the executable name, in this case kwrite, such that you don't get a huge list, but you get a filtered one. So list and then kwrite. Okay, we have 3 core dumps and all of those are present. Says the name of the executable, the process ID at the moment where the crash happened, and whatever, when the core file was generated, why it was generated, because we sent a SIG-SAG. And this shows information as rows in a table, whereas core dump CTL info will write a ton of data about each of these entries. Let's see how that looks like. There's a built-in paginator. So one dump, page down, stack trace of each thread, a ton of information in here. But there's also a row that says storage colon. So we're after that. Okay, and at least for me, the order is sorted ascending in timestamps. So this is the oldest and this is the newest. And then somewhere in here, there's also an actual timestamp. And with those, you can see which one is newer. So 1781299, I don't know, this looks like maybe Unix sticks or something similar. And then the newest is this one with 35 versus 30 versus 39 versus 29. So the last one is the one that we're interested in. In order not to use too much space, core systemd minus core dump generates dumps, but then also compresses them using Z standard. So we're going to use a temporary directory where we get this file from its storage from /var/lib, and we're going to decompress it using an Z standard. So let's copy from where it's located, and then it says present, which means that the file still exists, to the current directory, decompress it on Z standard. That's the command line on Z std. Let's see the sizes of these files. How do we do that? So compressed Z standard is 4.3 megabytes, whereas uncompressed is a third of a gigabyte. So very wise decision to compress these dumps. The compression ratio is almost 100 times. Next up, we can run GDB. So we're going to start GDB and then the core file and then the program. So we take this option. These vertical bars represent optional parameters, so either this or that or this, and we took the third option. So GDB, proc being the executable name, kwrite, and then the file. without any extension in this case. We're going to press C to continue without paging and enter to not use debug info D. And the debugger announces us that it's paused, so the process is not running, which means that we could do the actions that we can do when the GDB debugger is paused. So inspect local variables, list them, inspect arguments of current function, look at the core stack of the current thread, look at all of the threads, core stacks from all threads, globals, member variables of the current object, etc., etc., etc. Not all of these features are always available, either because the process is just not running, or because you don't have, you might, for instance, not have all of the CPP files with the source code. The core file might not be complete. Maybe you create a core file that doesn't contain all of these information, just parts of it. Maybe some of the ELF files, .so files, libraries, etc. existed on the system when the core dump was created, but then that core dump was created on a different computer, and you just receive the core dump and the kwrite executable. Some of these things you can do. If you have partial information, it's always preferable to have all of the information possible. Okay, not only the execution is paused on thread 0, which is the first thread, the most important thread, the graphical user interface thread, but the program is, while it's crashing, says program terminated with signal zigzag, segmentation fault. And we can do things. We can look at the backtrace of the thread 0. We can look at all of the other threads, backtraces core stacks from other threads, etc., etc. Next up, we saw that by default, when GDB is paused at a Qt symbol, maybe a constructor, maybe a place where there's a QString argument parameter to the current function, it cannot display it correctly. So it displays this like as 3 dots. Instead of saying it's a string, it's QString, and this is what's actually inside. For that, the kdevelop KDE Git repository has additional facilities where GDB can be enhanced such that it can inspect QString, for instance, symbols. Let's follow this part of the tutorial. So again, what we did previously, we start kwrite, we break at the kaboutData constructor where there's many parameters to this constructor. And we cannot see the value, for instance, of this argument, the argument text, but also home page address and bug address. We exit GDB and then we convince GDB to know how to list in human readable format those symbols. So for that, we'll need the kdevelop Git repository the simplest way for me to actually do it is to build the entire KDE Git repository using KDE builder. So KDE minus builder space kdevelop. 58 Git repositories to git clone, configure, make, and install. Okay, so KDE builder has finished kdevelop. At least it did the git operations correctly. CMake configure has failed for kdevelop, but that's not a problem. If we have the git clone of kdevelop, then that's more than enough. And we also know where KDE builder has git cloned the kdevelop git repository. And it's in the expected place, which is tilde/kd/src/kdevelop in here. At this point, we're looking for the full path of this directory. So plugins, GDB, printers. And we're going to create a configuration file for GDB, tilde/.gdb init. Let's create it. And just paste the contents in there. Have a trailing new line and replace this full path with this full path. Keep the rest of the text as is. So just this thing, you need to specify it correctly. Or you can just git clone the Git repository by using, for instance, this git clone URL. Or you can go download source code as a tarball or as a zip file. Okay, so now when we're going to run GDB, it should know how to display the value of identifiers of many important built-in Qt framework types. So let's just redo what we did previously. GDB kwrite. There's auto-completion and history also inside the GDB REPL. So you can go up arrow or not inside the same session. Like this. And then we're going to run. No. And now we have a totally different output inside the GDB. Let's actually look side by side at these outputs. Okay, so it could display in the correct human readable format the parameter component name. So we can see that this is a constructor, has on first position the this. Let's see if we can navigate there. So this is how the source code looks like. Constructor of k about data. there's a hidden argument on the first position, which is this, and then the rest of the arguments. Okay, so it could display component name, which is of type QString, could display name, which is also QString, version, that's QString. So previously it just had 3 dots, now it says the version between double quotes. Short description also QString. The license type, because it's an enum, it's part of the C++ programming language, so it could display that without our enhancements. And then the rest of the parameters, constructor arguments, are of type QString. So copyright statement with the correct value, text with some HTML, homepage, URL, and bug address with an email address. Okay. And now let's run a bit of a quick run through the capabilities of GDB. We're going to create a C++ program that does the sieve of Eratosthenes, one of the first programs that programmers write, which we're going to do using echo. So there's a file sieve.cpp, which looks as expected. And then we're going to compile it with this important command line parameter, which is -g, which means generate debug symbols. And then we're not specifying the optimization level with minus uppercase O. So the executable is not optimized, which is important when debugging. When you run executables and libraries that have been release optimized, the debugger will encounter various issues, like entire functions, for instance, free functions might be inlined, and then that will, of course, change the mapping between what's the actual executable source code, executable code, and then the source code. The executable doesn't really know that a function is being called because the entire body of that function is inlined inside the body of the caller function, and other optimizations. And when you ask the debugger to step one line, it might jump in a totally different place. Okay, we can run the executable. It outputs the prime numbers that are less than or equal to 30. GDB does have a manual, probably also an info page. Of course it does. And also inline help. So after you go GDB, you can write in here, I know, help. Okay. So just help lists a list of commands. Apropos, breakpoints. Okay. we're starting GDB and tell GDB to load the executable file from the current directory, which it can. Then we say start the process. No debug info D. The process is being run, monitored by GDB, but there are no breakpoints inside the executable. GDB doesn't pause anywhere. Because we have used the GDB command run. There's another way to do it, which is to use the GDB command start. Let's see exactly what it does. So it tries to identify the main procedure, which is the C symbol, exported symbol, the entry point main of the executable. Okay. We can set arguments before running run, as we did previously when we have set a file to be opened by kwrite. So let's do start. To start basically creates a breakpoint inside the body of the main entry point function, and then it probably runs run. I know. So it starts the process, a million of instructions run, and then line 25 inside sieve.cpp is hit, and the debugger will pause there. Okay, let's see how we step over. So that's next, or N. It says that it was on line post, debugger was paused on line 25, and now the debugger is paused on line 26, and that we have the source code file of this line. Okay, so we can run N a number of times. I'm using the history feature, which is up arrow key and then enter. So I have run next 1, 2, 3, 4, 5, 6, 7 times. Next doesn't step into, it's step over. Let's look a bit at the source code. So we were stopped at line 25 first. So this was the first breakpoint that we have hit. And then we said step over, go to line 26, step over, go to line 27, 28, 29, 30, and then the process is finished. We did not step inside this function call. We have never paused on line 5, 6, etc. So just step over a number of times until the process has finished. Okay, we're going to start it again. The same thing, there exists an executable which is called sieve, which is loaded inside GDB. There's a list of breakpoints. There's this breakpoint that we have created when we said start. Okay, and then we can use next or N to step over, but we can also provide a number of times to step over. So we can go N2. or N10. That will probably finish the execution. And it does. Okay, let's start again and see the source code. So by default, when the debugger is paused, it will, and if it can find the source code file, it will say which source code file, which line, and then starting from here, the actual source code line is written to standard output. If we want to look around, again, we can open the files, the source code file in a text editor, or we could use the feature inside GDB that's called list. So the same thing, we said list 10 lines around the current line where we are paused. So we're paused on line 25, which is this one. It lists that line. It lists the 4 lines after and the 5 lines before. So 10 lines in total. I'm not sure what list does, but list dot lists the current position. Ten lines around the point of execution in the current frame. And you can look as you were with the searchlight before and after these 10 lines with list plus and list minus. Let's see how that works. So list dot, and then we should see the next 2 lines, which is just squarely brackets being closed. So list plus, just one. Cool. We can change the number of lines to be listed. Something else than 10. We're reverting back to the default, which is 10. Probably if you close the GDB session, all of these settings that you do in here will be temporary and will be lost. Okay, and then let's look at step into. So when we're on line 26, 27, we should enter inside sieve of Eratosthenes. Let's see where we're currently paused. At line 25. So we're here. We should run step over twice and then step in. Hopefully that works. So N2 and then step into, which is the word step, this guy. And now we're at line 5 and we're going to run inside this free function sieve of Eratosthenes. Okay, let's list. And if we run help without any parameters, it says what types of help we can ask for. So there's help all, and then help and a one of these. So there's running, so we can go help and running. So you can go help space breakpoints, help space running, etc. Trace points. Continue, we used this. It's for running from the current place where the GDB is posted until the next breakpoint. How do we page in here? Enter. And step to step into. Step program until it reaches a different source line. I'm not sure what this text says. Okay, and then there's finish. Finish is probably stepping out. Okay, so we're now at the core stack has just one function. And from here we can go continue. Okay, let's also look a bit at the text user interface, GDB. The REPL looks like this. It is a text user interface, right? I don't know. Let's restart restart running. And we're going to use we're going after this command, which is TUI space enable. Let's find out this exact command. So for that we use help, and then we go text and then user. There's autocompletion. So help text minus user minus interface. And in here we can see TUI disable to exit the TUI source code window and status window, TUI enable to enter, TUI focus to change focus between these three windows. There's also the assembler view. There's registers. GDB is the debugger as you know it from other programming languages, from other integrated development environments. I know from Turbo Pascal, from Turbo C++, from Delphi, from Visual Studio, Visual C++, etc. Okay, we want to enable the text user interface. We're paused at line 25. We want this command, GDB command TUI space enable. We're presented with three different windows. The first one is this one with the source code window. There's the file name, the line numbers, and the syntax highlighted lines. Then there's a status window, and then there's the commands window. The status window has white background. Okay, let's go finish. To what? To nothing. Doesn't do anything. We're already inside the main. So we're in here. Okay, we're going to run next, which is step over 2 times. we should go to line 27, step into, go to line 5 probably. When the text user interface has issues, if GDB looks strange, press Ctrl L. It often has issues. I'm not sure what generates them, but if what you see on the screen is different from what you think the screen should look like, just press Ctrl L when you're in text user interface mode inside GDB. Okay, we want to step into, goes to line 5. The SRC window is focused because we can see that it has this greenish background around the window decoration. And in here we can use the keyboard keys to scroll. So the point where the execution is paused, you can see it in here with this upper than character, line 5. Also the highlight on the line with white background. But then using the keyboard key, you can scroll up and down. You can run the command info Windows, which will say that there's 3 windows. This one at the top called SRC and has focus. This one, just one single line called status, says lines 1. And then CMD, the next 13 horizontal lines, doesn't have focus. You can switch the focus from the CMD window from the SRC windows towards the CMD window, like this. The window decoration of this SRC window is different. The greenish highlight is missing. And now if you go up and down, we can see the GDB command REPL history. Okay. Let's see if we can break on line 11. So on this place where prime array, where vector at position I, we assign it value false. Help break. So break or B. And then location, thread, if, wow. We can provide an identifier. Uses the current execution address. We can specify function name, etc., etc. So break or B and then line 11. Says that there's a new breakpoint on line 11 sieve.cpp. We can see it in here symbolized with a B+. We're going to jump from line 5 to line 11 using continue. We can delete breakpoints, we can list breakpoints. Okay. And we can also inspect values of identifiers. So let's look into that. So help info. You can specify info and then an address. There's info breakpoints or info B, which shows the list of breakpoints similar to a tool window that you have inside a debugger inside an integrated development environment with the breakpoints. Fortran and Objective-C. Files being debugged, info space files, info frame for the selected stack frame, info locals shows all local variables, info main details about the entry point function main, info OS information about the OS data arc. I'm not sure what that is. Registers, CPU registers. Threads, info threads. All global and static variables with names matching regexp. Info variables. Info win lists information about the Windows syntax user interface mode. Okay, so let's go info and then locals. So there's n is not a local. We have prime, p, and I. And you can inspect the values of identifiers. And theoretically, you can also change values of some of the identifiers, which might be important. So print and then an identifier. You can inspect just one value inside an array. Let's see what the value is on position 2, which is the third element inside the vector prime, which is this thing. True. You can even run some things. I'm not sure what these things are. Maybe methods, maybe you can do very complex statements using print. You can do pointer arithmetics, etc. Backtrace. So we're on line 11 inside the function sieve of Eratosthenes, which was called by the function main. So up top sieve of Eratosthenes line 11, and then caller main sieve.cpp line 27, which is this guy. Okay, what is? Prime is a std vector, correct, of bool. So what is no C++ symbols and C++ mangling rules and the C++ programming language? P-type. And we're setting a watch point on I'm not sure what this is. Writing or reading from elements of prime. Another watch point for accessing the local variable I, which is the loop variable inside the for. So one is a hardware watch point, the other one is a watch point. All of these are breakpoints. We have breakpoint 7 for I, breakpoint 6 for prime of I, and breakpoint 5 was this guy for line 11 inside Sivo Eratosthenes free function. Info breakpoints. So breakpoints 7, 6, and 5. And then for if the execution is paused on one of the breakpoints, it says additional information. It says breakpoint already hit. It says if the breakpoint is enabled. Okay, and then we can run this thing a million times to see what it does. So we're inside the vector. We're inside the watch point 6 with a prime of I, where it does what sort of an operation. Let's put the focus back into the SRC. So focus, SRC. Using the up arrow key, I'm looking around. So what is this? It's an operator bool. Yeah. It's what it's expected. So some access to prime of I will trigger the watch point, which is actually breakpoint and breakpoint number 6. And then we have, it says that the value has actually changed from true to false. Okay, let's clear, so if you just clear one breakpoint, let's do that. Clear breakpoint. Let's see the help for clear. So clears breakpoint at specified location. The location being either an identifier or if you want a file name, you probably need to specify the colon there. So clear sieve.cpp and then colon line and number. And then info breakpoints again. And now we only have two breakpoints, the watch points. Okay, finish is stepping out of the free function. And now it I'm not sure what it says in here. So it's still in STLB vector. Yeah, it didn't step out because we still have a ton of breakpoints in here. Prime of I is going to be changed a ton and I is going to be changed a ton. Okay, Control D, Y. You can start the text user interface immediately using the --2e command line parameter to GDB. And if you don't like this very verbose text at the start of GDB sessions, there's a command line parameter to hide this banner. And that's -q. And then you can run GDB in non-interactive mode. You can give GDB a ton of commands that GDB will execute. You can say, open this executable, set these command line parameters to the executable, start a process, log verbose, write all input and output inside GDB to this file, and then run a ton of GDB commands. I know, start, and then break, and then continue, etc. BT. So this was it. This is how to use GDB, but then applied to KDE programming. We have used the kwrite KDE graphical user interface text editor, which is a simplified version of KDE Kate. It's useful to know how to use GDB. Sometimes you don't have a full-blown integrated development environment. Sometimes the debugger inside an integrated development environment is not that great. Many integrated development environments have a debugger that's actually a wrapper around GDB, and the wrapper is not that perfect. Sometimes if the debugger crashes inside a integrated development environment, and if you know that the debugger is actually GDB, by going directly and using directly GDB, maybe it won't crash on you and you will be successful in your endeavors. Sometimes you're connected remotely over SSH, within an SSH, within a tunnel, within a, and you have access to GDB. Or maybe you're inside a container, inside a Flatpak app, etc., etc. And in cases like those, GDB is probably your only chance. So it's useful to know how to do from the GDB command line and GDB REPL the things that you normally do inside an integrated development environment debugger support. Thank you.